Mr. Quagliotto here, and for the remainder of this chapter we're going to be talking about specific segments that we can find inside of triangles. These include perpendicular bisectors, angle bisectors, medians, and altitudes. But for today we're just going to focus on perpendicular bisectors and then later on angle bisectors. The first thing is a perpendicular bisector, which is just a line that is perpendicular to a segment at its midpoint. And I'll show you in the next video how to construct this. I suggest that you have out a paper, pencil, and compass to follow along. I'm now going to show you how to create a perpendicular bisector to a line segment. So we're going to start by drawing a line segment. And it doesn't really matter the length of the segment. I'll call my endpoints A and B. And what we're interested in finding here is some midpoint where when we draw a line, every point on that line is equidistant from A and B. So for example, if I were to take a line, and let's say this is our midpoint, splits it directly into two, and if I were to take a line and draw it like this, and put some random point here, well, as you can see, this point is closer to point A and further from point B. So you should be thinking, well, this line should probably be straight up and down, and that would be the perpendicular line. To construct this, we make use of our compass. And what we have to do is put the endpoint on one of the sides of the compass and make sure that the compass stretches past halfway point. Otherwise, this won't work out. And we make some markings like that. And then we flip it around, put the compass on point A, and without changing the compass at all, make the same markings. You then take your ruler and you connect the 2 points where those arcs intercept. And this new line is your perpendicular bisector. It goes directly halfway between line segment AB, and it forms a 90-degree angle. You can construct the perpendicular bisector to a triangle by focusing on each of its sides. So we're going to focus on side AC and construct that perpendicular bisector with the same process that we just used. So we first start by drawing our arcs. After drawing our arcs, we can then connect the points where they intersect. So we're going to connect to this point here, to drop our perpendicular line, or perpendicular bisector. What we'll notice about this is any point that's on this line, the perpendicular bisector, is equidistant from the endpoints that we bisected, the segment that we bisected. So for example, if we take a point right here, this point is the same distance to A as it is to C. This brings up the perpendicular bisector theorem. On a plane, if a point is on the perpendicular bisector, so here's our perpendicular bisector, of a segment AB, then it is equidistant from these two endpoints. i.e., if CP is the perpendicular bisector of AB, we have that AC is equal to BC. This quick example has us finding the length of side AB. Now, what we can come up with here is, well, first of all, we see a perpendicular line that bisects the segment AC. We know it bisects because AD is congruent to DC. They're equidistant. So this is the midpoint. We have a 90-degree angle. Using the property we just learned in the perpendicular bisector theorem, we have that these two distances, AB, is equal to the distance of BC. So we can set up the equation 3x is equal to x plus 14 and solve for x. Subtract x from both sides and 2x is equal to 14, so x must be equal to, we're dividing both sides by 2, x is equal to 7. So when it asks us to find the length of AB, we've got 3 times 7 is equal to 21. The converse of the perpendicular bisector theorem is just the same theorem the other way around. So you're looking at the conclusion implying the hypothesis of the last one. Our conclusion in the last was that the segments AD and DB were equal, so we're going to start with that here. If AD is equal to BD, then we have that D lies on the perpendicular bisector of AB. Pretty easy, just the other way around. In this example, we're given that JN is the perpendicular bisector of MK. So that means that JN splits MK into 2 equal pieces. Now it tells us that NK is 24, so we can say that MN is also 24 because a perpendicular bisector splits a segment in half. So already, well, MN is equal to 24. Reason, definition of perpendicular bisector. As we just learned with the perpendicular bisector theorem, if we have a perpendicular bisector, we know that MJ and JK, those two other sides of the triangle, must be equal in length. So these two values must be equal. So we can solve for JM by first solving for x. 5x plus 1 is equal to 3x plus 5. Subtract 3x from both sides, and subtract 1 from both sides as well. So 2x is equal to 4. X must be equal to 2. So by plugging this back in, 5 times 2 plus 1 is equal to 11, and 11 would be the length of JM. The reason, of course, as we just said, was the perpendicular bisector theorem. Now we're asked to find ML. At first this might seem a little strange, but it tells us that these two lines are congruent. So really we can set 8x is equal to 7x plus 2. Solving, subtract 7x from both sides, and x is again equal to 2. Now, we already knew x was 2. I just wanted to check yet again, but really this just turns into plugging it in. 8 times 2 is equal to 16. And the reason is because these were congruent. You could have also used the converse to the perpendicular bisector theorem, but it really wasn't necessary in this example. A triangle has 3 perpendicular bisectors. We've got one right here, 2, and 3. These perpendicular bisectors meet up at a point, and what we call this point is the point of concurrency. The interesting thing about this point is that if you take your compass and place it directly in the center and match it up with one of these vertices, and then draw a circle around it, that circle will actually go through each of the vertices of the outside triangle. So this point represents the direct center of a triangle. This point of concurrency has another name, and we call it the circumcenter. The final theorem in this lesson is the concurrency of perpendicular bisectors of a triangle. And it sounds like a mouthful, but really all this means is when you take perpendicular bisectors of the triangle, so for example we have this perpendicular bisector, and this last one here, and you have that point of concurrency in the center. You then take a point P and draw segments from that point to each of the vertices. What you end up with is that these red or orange colored segments are all equidistant. So P is equidistant from each vertice or vertex of the triangle. Hence, PA is equal to PB, which is also equal to PC. So if I were to tell you that KQ was equal to 18, you would be able to deduce that QM and QL was also 18 by this fact. And that concludes this lesson, but you may want to go back, rewind, write some of these definitions and words down because this is more of a wordy section, so just be aware of that and come into class ready to practice some of these concepts that were demonstrated to you today.